Section 8.2, the pressure temperature diagram. So again, we have pressure here, we have temperature here. The pressure is in 1 bar, so over here this is 1 bar. And then if we are looking at the solid, liquid, and gas phases of a substance, you will see the pressure always increases as temperature increases. Okay, look at the slope here, the slope here, the slope here. dP over dt is always positive, with one exception. Look at this red dashed line. This is water. Okay, we'll get back to that. Now let's look at the three phases. Make sure you can draw a phase diagram of a typical substance, and then you can make some changes for water. This is the triple point. The solid, gas, and liquid coexist. This is the triple point. This is a triple point temperature. This is a triple point pressure. Now let's look at this line. This line tells you what the sublimation point is between solid and gas. This line tells you what the boiling point is between liquid and gas. This line is the melting point between solid and liquid. So you can tell that if you change the pressure, you can change the sublimation point and the boiling point significantly. But to change the melting point, it's hard. Why it's hard? It's simple. The molar volume of solid and the molar volume of liquid are very small. It's very difficult to change the chemical potential of the solid and liquid by changing the pressure anyway. However, it's very easy to change the chemical potential for a gas. Remember the equation? The chemical potential of a gas is equal to mu naught plus RT times the logarithm of P over P naught. So if you double the pressure from 1 bar to 2 bars, you increase the chemical potential by RT times ln2. R is roughly 8, temperature, let's say 300 K, and then you get 2.5 kilojoule there times ln2. ln2 is 0.7. So if you double the pressure from 1 bar to 2 bar, you actually increase the chemical potential by nearly 2 kilojoule per mole. On the contrary, for solid and liquid, if you increase the pressure from 1 bar to 2 bar because of their small molar volume, usually it's just, let's say 20 milliliters per mole. If you use 20 milliliters per mole times the pressure change, 1 bar, that's pressure change. The resulting chemical potential increase is only 2 joule per mole, or 0.002 kilojoule per mole. So if you increase again the pressure from 1 bar to 2 bars, the chemical potential increase of the gas is roughly 1,000 times that of a liquid or solid. Well, only because the molar volume of the gas is much larger. Now let's look at process A. If you look at A is a bit under 1 bar. So this is a isobaric process with lower than 1 bar pressure, and then from lower temperature to higher temperature. First you have the solid, and then you have the melting point right here, and then it's a liquid, and then boiling point, and you have a gas. That's A. What about B? B is very simple. You just further lower the pressure so that the gas chemical potential crosses the solid chemical potential before the liquid. And then if you look at B, solid, sublimation point, gas. Now let's examine C from here. Okay, this is isothermal, constant temperature. And first it's just a gas. You cool it down, it becomes liquid. You further cool it down, it becomes a solid. Now let's look at D. D is simple, from gas to liquid. It's condensation. It's called condensation from gas to liquid. Well, at in this case, at a higher than 1 bar pressure. Well, you can also do this at exactly 1 bar pressure, and then you have the standard boiling point. Under 1 atm pressure, it's called normal boiling point. This point D can also go to this point, from other steps. That's fine, because P and T are just state functions. So you can go here, you can heat it up, and then increase the pressure Now what is this? This is supercritical fluid. And then you lower the temperature of this supercritical fluid. You go back down here, lower pressure. You go to this point. You get this liquid. So you can go from gas to liquid by just changing its temperature or lowering its temperature, or you can even increase its temperature, increase its pressure to get supercritical fluid, have some fun, and then lower the temperature, lower the pressure, and then you get the liquid. So make sure you can just describe this ABCD processes. Just a reminder, when the temperature and pressure are higher than the critical temperature and pressure, you have a supercritical fluid. This supercritical fluid is between a liquid and gas. The density of a supercritical fluid is usually 30% of the liquid. And 300 times larger than the gas. So if you're just talking about the density, the supercritical fluid is closer to the liquid. But liquid usually has a finite volume. It's actually easy to change the volume of a supercritical fluid. So in that sense, it's more like a gas. Anyway, it's in between. The use of supercritical fluid. Do you drink decaffeinated coffee? In industry, they use the supercritical fluid of CO2, carbon dioxide, to take the caffeine out of the coffee beans. Alright, so how does temperature change when heat flows into a solid substance? Well, it can be melting point, it can be sublimation point. But if the pressure is high enough, we observe the melting point first, and then we observe the boiling point. So this is what you're looking here. When heat flows into a solid, well, the temperature goes up. Oh, by the way, we're looking water. At 0 degrees Celsius, you provide more heat. How does the temperature change? It's not going to change. It's going to be a constant right here. It's a constant. Why? The heat is used to melt the ice. This is a so-called enthalpy of fusion. Okay, under constant pressure, it's enthalpy of fusion. Under constant volume, well, that's hard to maintain. But in case you're talking about constant volume, this is internal energy of fusion. And then we have liquid water at 0 degrees Celsius after all ice is melted, and then we keep adding heat to the liquid water. Its temperature goes up, and then at this temperature, 99.98, I don't know why. It's under 1 atm pressure, it should be 100 degrees Celsius. If it's 1 bar pressure, it should be 99.8 degrees Celsius. So anyway, I grabbed this picture from the internet with the copyright for non-commercial use. Okay, again, over here, this is a wide range because we'll have to provide a lot of heat to convert liquid to gas. And after that's done, you're heating up the gas. Now let's look at this line, and this line. If you look at the slope of this line, it's dt over dqp. dt over dqp. dt over dqp. What's the physical meaning of dt over dqp? Well, you have to take its reciprocal. The reciprocal of dt over dqp is dqp over dt. That's just Cp. That's heat capacity. So the reciprocal of the slopes of these three lines are the heat capacity of solid, liquid, and gas. And over here, well, what's the physical meaning of this range? That's the enthalpy of fusion. This wider range, that's enthalpy of vaporization. So you can look at this, it's roughly 6, that's the enthalpy of fusion. Look at this range, I think it's about 41, that's the enthalpy of vaporization. Water, PT diagram of water. Again, this is water, ice, water vapor, liquid, positive slope, negative slope. Actually, this slope should be very negative slope, so it's steep. It should be very steep because the molar volume of ice and the molar volume of water, liquid water, are very small, and that's why this PT, dP over dt slope should be very, very negative. So it should be like that. Okay, but anyway, yeah, it should be like this. Okay, I think it's drawn this way just to emphasize, there's a negative slope, more apparent negative slope. Now let's look at this. At 1 atm, you have the boiling point, and also you have the melting point. 0 degrees Celsius, that's the melting point. Between ice and water, between water and gas, that's the boiling point. Over here you have a triple point, 0.01 degrees Celsius, and the water vapor pressure is 0.006 atm. Again, I mean, in the winter of Ellensburg, you can observe the triple point. Although the pressure is 1 atm or 1 bar or close to 1 bar, this is because the water vapor pressure is 0.006 atm. The pressure of nitrogen, oxygen, they do not really matter. Now let's look at water again. Okay, so this time it's still the phase diagram of water. If you just look at this region, it's just typical phase diagram of water. Look at this. Look at this line. This line actually has a negative slope, and it's nearly like negative infinity. Okay, very, very steep. Now, what if we increase the pressure from like 1 bar? So I think somewhere here is 1 bar to 10 bars, to 10,000 bars. Okay, to even higher, and then you have more solid phases. Okay, this is because if you keep compressing ice, okay, with very high pressure, well, it will have to adopt a more compact structure. So all those structures, so I'm pretty sure this Xi solid phase has the smallest molar volume. All right, and again, this is the supercritical fluid. All right, we're done with 8.2.